సరే ఎప్పుడు ఆపాలో ఒక 5-10 minutes ముందు చెప్పండి. ఎప్పుడు ఆపాలో 10 minutes ముందు చెప్పండి. లాస్ట్ డే ఎప్పుడు అనేది. ఓకే, అటైతే ఓకే వెళ్తాయి. I think so. Okay, so let us say we have two systems, system X and system Y. System X classical state is sigma, system Y classical state is gamma. So combiningly we are viewing XY as single system. What is the classical state set of X comma Y system? Cartesian product of both, okay, respective states. What next one is, we are performing U1 operation on system X, independently U2 operation on system Y. What is the combined operation on system XY? It is given by some other operation like Cartesian product here by some other operation. Now can you tell me, if at all we perform this operation, what is going to be the order of that operation? Okay, we'll see with examples. After that, I'll ask a question. Okay, maybe you will understand that operation properly. Okay, so tensor product. So you are given a matrix AB, another matrix CD. This is tensor product symbol. Okay, what is tensor product of this? So it is, this is first matrix. First matrix you write as it is. This is my first matrix. So next to each element of first matrix, you copy second matrix as it is. What is second matrix? CD. Here also you copy CD. Now elements you multiply, but same row you keep it. This is like a scalar multiplication. A into C, AC, A into D, BC, BD. This is called tensor product. This is called tensor product. Now that we can extend to any. So I'll show you through some examples. Okay, we'll come back to this. First let us see. ABCD. What is tensor product? This only. Is that okay? Okay. Now what is tensor product of this? Can all of you try and tell me? V1, W1, V1, W2. Is that okay? So as it is, I have written second matrix, copied. V1, W1, first row. This is second row. This is third row, fourth, like this. Is that okay? Okay. So all of you calculate Hadamard, tensor, Hadamard. Hadamard. Hadamard, we know what is the matrix, no? So 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2, tensor 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. Okay. First matrix you copy as it is. So equals to first matrix 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. As it is, I copied. Okay. Then don't ask why did you give space. You know the intention, no? Okay. Okay. Second matrix as it is, you copy. So it is 1 by root 2, 1 by root 2, 1 by root 2. But next to every element of each element of this. So similarly here. Okay. Total, how many elements we get? 60. So first system, it is single qubit operation, 2 by 2 order. Second matrix, 2 by 2 order. What is the order of resultant tensor product matrix? 4 by 4. That's what I asked. Okay. Okay. This is 2 by 2 means we know that how many states are there? 2 possible states. Second system is 2 by 2 means again there are 2 possible states. Cartesian product contains 4 states, 2 into 2, 4. That means without knowing what is tensor product also, we should be able to say that at least 4 by 4 matrix we get as answer, no? Why? Because that 6 by 6 you only answered, no? One naam ke vaste matrix we have taken, okay? Okay. Is this okay? Now tensor product is it clear? What is tensor product of this? General. How many rows it contains, you please tell me. M into K. Then correct. How many rows if you are able to, means number of columns is 1 only. Rows you are given correctly. Okay. All of you got this answer? Oh, here 1 by 2 is taken out. See, these 4 elements are same as these 4 elements, no? 1 by root 2 into 1 by root 2, 1 by 2. This also same, no? Here sign change. If you see here, 1, 1, 1 minus 1. Here also 1, 1, 1 minus 1, 1, 1, 1 minus 1. Here sign change, ulta, minus 1, minus 1, minus 1, 1. 1 by 2 taken outside. The tensor product clear? Like this, anything you should be given 2 matrices, whether you will be able to find tensor product? Yes, okay, that is tensor product. Now, what are the notations used for tensor product? Now we know how to calculate tensor product. In textbooks, if you see, these are different notations used. So this is first system state. This is second system state. State means again it is a column matrix only, no? Matrix 1, matrix 2. Tensor product is, people write it this way. Sometimes they also write it this way without explicitly mentioning this symbol. This symbol is not written, but still we should understand it like tensor product. Sometimes what they write is, they don't even write it completely. Ket pi, ket psi. That they remove directly, they write it inside like this. Still we should understand it the same way. Different authors, they use different style, but all mean the same. Okay. Is that okay? Okay. Now all of you calculate tensor product of ket 0 with ket 0, ket 0 with ket 1, ket 1 with ket 0, ket 1 with ket 1. All for 1 minute. Is it clear? What question clear? Ket 0, tensor product, ket 0. Similarly, other 3 possibilities. Ket 0, tensor, ket 0. What is ket 0? 1, 0, tensor, 1, 0. Okay, this I'll explain. Other 3 you please try. 1, 0, 1, 0. Is that okay? which is same as ket 0 tensor ket 0, which is that means already we have written, we can directly write it as which is same as ket 0 or we can also write it as ket 0 0. All are same, no notation. So similarly other ket 0 tensor ket 1 you please calculate. That's all. Ket 1 tensor ket 0. That means whether I write it this way or this way, both are same, no? Okay. Now we'll try to understand 2 qubit operation. 2 qubit operation. 2 qubit operation means what is the corresponding matrix? 4 by 4 matrix. 4 by 4 matrix. And that operation already we have seen. Input is input output. Input is 0 0, output is 0 0. Input is 0 1, output is 0 1. Input is 1 0, this is 1 1. 1 0. This is in. Now which 2 columns are same? It is same as this, no? Both are equal, no? Okay. Here in the output, whatever is this column, same thing you copy it. But here it is 0 0, here 1 1. But here 0 1, here 0 is there means here 1 is there, here 1 is there means here 0 is there. Can you see some pattern here? When it is inverted, you first one is 1, second one is inverted. First one is 0, nothing. Same thing we have written. Is it okay? Now, input, in the input, if the first element is 1, second element is inverted. Otherwise, same input is given as output. Is it okay? 0 0, what is output? 0 0. 1 0 1 0 1 0 1 1 1 1 1 0. This we can say based on this control we are changing this. What change it is happening? 0 to 1 it is going, 1 to 0 it is going. It is like not no. And this type of operation is called controlled NOT operation. Controlled NOT. That means it is 2 qubit operation or single qubit operation? 2 qubit operation. Okay, it is a 2 qubit gate, controlled NOT. Based on some control, we are performing NOT operation. That here also, this is control, we can call it as target. Here also control, this is target. Control, target, control, target. Control is same in both input side and output side. Target in the output is flipped. If control in the input is 1. That's all, no? Okay. So, this is the operation. This should be 4 by 4 matrix. Why? Why? 2 qubits, no. 2 qubits means how many states? 4 states. These are the 4 states, no? Or these are the 4 states. That means what are the possible inputs? Either 0 0, 0 1, 1 0, 1 1. Okay. Now you tell me, you should be able to tell. If ket 0 0 is given as input, what is the output it has to give? Like that, the other 3, you know, no? So can you verify for at least one? Ket 0 0, is it giving the same answer? Ket 0 0, okay. First circuit diagram for this is this. First column, that's all. First column. Yes. Here, this is the circuit diagram for this. This dot, no, it denotes control. That means this bit. This symbol is XOR symbol, no? So if you want to find this answer, how? One way is 0 XOR 0 what? This 0 is it okay? What is 0 XOR 1? 1. What is 1 XOR 0? What is 1 XOR 1? 0. Same thing, no? So target is simply XOR of 2 input bits, no? That's why this is target. This is control, this is target. What does this control say? If I am 1, then only you change my target. It is 2 qubit. Why? This is 1 qubit, this is second qubit. No, 2 qubits are mentioned. X and H, only single qubit. That's why only one line is there, no input. Is the difference clear? Okay. Now can you tell me, if Q0 is 0, Q1 is 0, Q0 is 0, Q1 is also 0. What is the answer we get here? 0, 0. How did we get that? This is 0, 0 means what is the answer? Ket 0, tensor ket 0. That is actual input. Ket 0, tensor ket 0 is the input. Is that okay? Okay. Now what is happening? This is control. Control is 0. Target is changed or not changed? Not changed. That's why same 0, 0 we should get. You can see this. Ket 0, 0 is, this is the matrix. What is the circuit? Circuit is C0 is, this is the matrix. What is Ket 0, 0, 1, 0, 0? You multiply. Which column we get as answer? First column. This means again this only, no? We got. Similarly, you can verify for remaining 3. Now, if I go for measurement, what is the probability of getting 0, 0? 1. Always we get 0, 0 only, no? Here also I get 0, here also I'll get 0. That means always we get 0, 0 as outcome, no? So probability of getting 0, 0 is 1. That means always we get 0, 0. What is the probability of getting 0, 1? 0. 1, 0? Because 1 has become 1 means other 3 must be zeros, no? 1, 1 is also 0. If the measurement gives 0, 0 with probability 1, that means other 3 we don't get. In this case, what is the answer? How we got, we are trying to understand. Okay. 0, 0, 1, 0. Again, matrix is what? We know this is the matrix. 1, 0. Is that okay? This is nothing but what? Fourth one. Fourth one is Ket 1, 1. Okay. Measurement gives what? 1, 1 with probability 1. Other things we don't get. So similarly, the other. Is C not clear? Okay. Now, the other way of viewing it is, other way of viewing this matrix is, so that you can easily remember is, measurement gives classical output, but with some probability. Alpha Ket 0 plus beta Ket 1 means mod alpha square is the probability of getting 0. Finally, we get either 0 or 1, but we are only calculating what is the probability of getting 0. It is like tossing a coin, no. Okay. Now, what is? The other way of viewing that matrix. This is control not matrix, no? This is 4 by 4 matrix. 4 by 4 matrix. This is 4 by 4 matrix, no? I can view it as, I can divide it into 4 equal parts. Then here it should be 2 by 2, 2 by 2, 2 by 2, 2 by 2. Any control operation, we can represent it as identity here, corresponding identity. This is only zeros. This is only zeros. Here, control not, after control not operation, not means it is X gate, no? The actual operation X. Now, if you, can you please write down this? What is I means? 1, 0, 0, 1. First part, okay. Below this side, right? Okay. First part is 1, 0, 0, 1. Second part means 0 means all zeros, 4 zeros. Second part is, third part is 0, 1, 1, 0. That's what is our matrix now. Now, not only for X, this you can do for any control Y also. Y, if they tell what is the matrix, then you can talk about control Y, Z also, H also. Your paper also control H is there. I saw that. Okay, no. Control H also we can talk about. Is that okay? That is called control not, control Hermod, control Y, control Z. Any gate we can apply control. Similarly, again, control not. Can you tell me what is control not? Control. Okay, good. What is control not? Now you know the procedure, no? Control not means it is going to be 3 qubit. Control not is 2 qubit. Again, control means 1 qubit extra. It should be 3 qubit. 3 qubit means 8 by 8 matrix. Are you? That's all. That is better even. 2 power 3. How many qubits are there means that matrix order is 2 power that much. So now can you write matrix for control not? So it is 8 by 8 matrix. Here it is 4 by 4. Here it is 4 by 4. This is 4 by 4. Here 4 by 4. Here identity. Identity means 1 0 0. This 4. Here all zeros. 4 0. Here it is again all 4 zeros. Here it is. What is this matrix? Controlled control not. Controlled C naught. I can consider it as controlled C naught. C naught, what is the matrix? This values you copy. 1 0 0 1, 4 zeros, 4 zeros, 0 1 1 0. This is the control not operation. What is the other popular name for that? You find out. Okay. So like this, we can define any controlled operations. Not only C naught. See, I have given 2 examples for single qubit gates. One is X, one is H. Similarly, we can have Y gate, Z gate, S gate, T gate, so many are there. Similarly, I have given 1 example for 2 qubit gate, C naught. Not only 1. Now, control Y means again you have got 1. Control Z means 1. Like this, many you got no. Next, 3 qubit gate also 1 example I have given. Is the procedure clear? Okay. Next one is, now at least 3 gates we are familiar. One is X gate, one is Hadamard gate, the other one is C naught gate. So with this, so far we used only single qubit gate in our circuit. We have not used 2 qubit gate, and we try to use 2 qubit gate also in our circuit. Okay. Okay, before applying that, you try to see, we are viewing n system together as single system. N systems together as single system. Then first system, it has some classical state. Second system has some classical state. Nth system also has some classical state. What is the classical state set of combined system? Classical state set. Cartesian product of all these n sets. What is the unitary operation corresponding to this entire system? Tensor product of all these n operations. Like here you can see now. Answer is not displayed here. Okay, this is the answer. Is that okay? First system U1, second system U2, last system UN. It is given by tensor product. We know what are classical states, what are operations. That much only we need know. Okay. Next one is, okay, so these are the first system I am performing some operation, second system I am not performing anything. Sometimes I have 2 systems. First system only I apply some gate. It is like I have some circuit. Here I apply Hadamard gate. Here something is there. Here I don't apply anything. Here only I'll apply X gate. See, are you getting? Here I'll apply X gate again. In this case, I am not applying any gate, no. It is not applying anything, is applying identity. Identity means it doesn't change the state, no. Are you? So this is Hadamard, this is identity. Combined operation is nothing but Hadamard tensor I. That's all. When some operation is missing, that you can replace with identity operation. That means no change. That's what here. One side, that one side, this the other side. And the same thing, whatever tensor product we discussed, this is more mathematical, formal way of defining that. What is this AB? AB is all possible classical states. This is the corresponding ket notation, corresponding state. And what are this? What are this? That is A into C, B into D, we are writing no, that entries. I think maybe once you have more familiarity with the Dirac notation, it will be more clear. Okay. So these are other ways of this already I mentioned. Now we'll see if we are given a state, 2-qubit system we talk about, we are given some state, whether that state can be written as tensor product of two individual system states or not. I give you 2-qubit system state. Is it possible to write it as tensor product of first system state, tensor product, second system state? That's what we try to understand. Okay. Now let us take this state. Is it 2-qubit or single qubit state? 2 qubits. Okay. Now what is question? Is it possible to write it as tensor product of first system state and second system state? Okay. So finally, what is given to us? 1 by 2, I by 2, minus 1 by 2, minus I by 2. This is given. Now, is it possible to write it as AB tensor product CD? That's all, no? A, B, C, D values, if at all we are able to find, then we say that yes, it is possible. Otherwise, no. No is the answer. Is the question clear, first of all? Okay. Okay, I think later you can try. I'll directly give you the answer. Okay. Let us see this. 1 by root 2 ket 0. First system state, you can say it as 1 by root 2 ket 0 minus 1 by root 2 ket 1. That means what is A value? What is A value? 1 by root 2. What is B value? Minus 1 by root 2. What is C value? 1 by root 2. I by root 2. Now you please cross verify whether we are getting the same thing or not. This is 1 by root 2 into 1 by root 2. 1 by 2, correct. 1 by root 2 into I by root 2. I by 2, correct. Minus 1 by root 2 into 1 by root 2. Minus 1 by 2. Minus 1 by root 2 into I by root 2. Minus I by 2. Correct only, no? That means this system state, x comma y, we are viewing it as a combined system. Combined system state, we are able to write it as tensor product of individual system states. That means what? In that case, we say that though we are combining, they are naam ke vaste combining. That means x and y, they have no relation at all. Then we say that x and y are independent system. This is independent state. This type of state, we call it as product state. Product means tensor product state, you can assume. Okay. Now, is it product state or not? Product state. Now you tell me, is it product state? No. Here it is impossible to write it this way. Okay, 2 minutes we will try to understand why it is not possible to write it this way. If assume that it is possible to write it that way. So what are the values we have? 1 by root 2. 0, 0, 1 by root 2. Correct, no? If at all I am able to write it as AB tensor product CD. That means AC, AD, BC, BD. Is that correct? If at all I am able to write it by contradiction, I am assuming that yes, it is possible to write it this way. If at all able to write means then I should be able to represent it this way. Now you tell me what is value of AD? What is AD? 0. When does AD become 0? At least any one of them should be 0. Both 0 also fine, but at least one should be 0. If assume that A equals to 0. If A equal to 0, AD is 0. But AC in this case, but AC should be 1 by root 2 according to this. It is a contradiction or not? If A is 0, AC 1 by root 2 we never get. That means it is not possible. A 0 is not possible. What is the other option? D 0. If D equal to 0, then BD equal to 1 by root 2, it is never possible. That means what? A equal to 0 is not possible. B equal to 0 is, D equal to 0 is not possible. Then we say that it is impossible to achieve that. We have got a contradiction. It is proved by contradiction. Okay, I have not detailed all steps, but this method is proved by contradiction. Is the procedure clear? Okay. Other side, if you want, why did you take this? Means I will take BC, same thing, no? BC equal to 0, B equal to 0, or C equal to 0. B equal to 0 means BD should be 1 by root 2. Here we get contradiction. C equal to 0 means AC should be 1 by root 2. Here also we get contradiction. That means however you take, it is impossible to write it this way. Then we say that though they belong to different X and Y, that system is somewhat not independent like previous case. There is some kind of relation between the two. If you make some changes here, definitely there may be some changes in the other case. And that type of state, we call it as entangled state. That is only entanglement. Entanglement means it is not product state. That's all. Now, formally, you know what is product state. Given a quantum state, if you can represent it as tensor product of individual system state, that is a product state. If you are not able to write it, then it is entangled state. In entangled state, one is going to affect the other. In fact, there is, if you make some changes here, irrespective of physical distance, automatically some changes will happen in other. That only we call it as entanglement. Now, formally, superposition means linear combination. Entanglement means it is not product, tensor product state. Like this, not only this, 1 by root 2 ket 0, 0 minus 1 by root 2 ket 1, 1. This is also, okay? 1 by root 2 ket 0, 1 plus 1 by root 2 ket 1, 0. That also, 1 by root 2 ket 0, 1 minus, like this, different states, 4 states are there. They are called Bell states. All 4 Bell states are examples of entangled states. Here, what is happening? The probability of getting 0, 0 when I go for measurement is how much? 1 by 4. Is it same as probability of getting 0 into probability of getting 0 here? 1 by 2 into 1 by 2. What is probability of getting 0 by 0, 1? 1 by 4. Is it same as probability of getting 0 here and the probability of getting 1 here? Correct? No. 1 by 4 into 1 by 2 into 1 by 2, 1 by 4. That means if the combined system state probability is product of individual system, occurrence of individual system state probabilities, then that is called product state. At this point, is it clear? Or, what I am saying is, what if I go for measurement, what is the probability of getting 1, 0? 1 by 4. That value is same as, first system is in state 1, no? What is its probability? 1 by, here all are 1 by 2, so no confusion I think for you. This is 1 by 2. What is the probability of second system in state 0? 1 by 2. 1 by 2 into 1 by 2? 1 by 4. We got, no? Then we say that, like that, if it is true for all, then we say that it is a product state. Like that, it is not happening here. That's why it is entangled state. Is this okay? The moment I say entanglements, are they independent or not independent? Not independent. Not independent. They share some kind of relations. Okay. This is also for 3 qubits. This also you can show that it is entangled. Okay, no, it is entangled. It is not possible to write it as tensor product of 3 systems, states. And this also you can 0, 1, 0. This also not possible. This one, what is ket 0, 0, 1? Can you write a column vector for that? 0, 1, 6 zeros. Okay, thank you. Okay. Now, is it possible to write it as tensor product of first system state, tensor product, second system state, tensor product, third system state? Is it possible? Okay. What is ket 001? We know that it is 0, 1, 6 zeros. Now ket 001, you find out what is ket 0, tensor, ket 0, tensor, ket 1. All of you calculate this. Equal. First you calculate any two. This two. This is equals to what is this? 1 0. This we have already calculated. No 1 0. Tensor 0 1. This two we calculate. How much? 1 000 no? Tensor 0 1. It is. Now this is first system state, this is second system state, this is third system. I am able to write it as tensor product of individual system states. No. Hence it is a product state or entangled state. Product state. They are nowhere related. नाम के वास्ते together. Okay. Okay, there are some examples you can try. This also. Okay. Now, this entangled tensor product, is it clear? How to calculate tensor product? What is entangled state or what is product state? Is it clear? You are given a quantum state. If you can represent it as tensor product of individual system states, then we say that that state is a product state. And the corresponding systems are independent. If it is not possible to represent it that way, then we say that the systems, they share there is some relation. They are not independent. There is some kind of correlation between the two. Okay, then we say that that state is entangled. Okay. Now I don't explain anything. Can you try this? What is the answer for this? Okay, you only try. I don't know whether you can. What is input state here? Ket 0. Ket 0, ket 0. That means what? What is the matrix? All are same. Because tensor product different way of representing, and this is matrix form. Now first system H, second system H. There is no relation between these two. No, we can easily see here. So what is the combined operation in these two? First system you are performing some operation independently. Second system you are performing some operation. What is the combined operation on this system? Tensor product H, tensor product H. Already we calculated that value. Yes. 4 by 4 matrix we got. No. That is what. Now this is what? C naught. Control naught. We know what is the matrix. Again this is H tensor H. Again we know what is the matrix for that. Already calculated H tensor H. Based on this, can you tell me what is the combined matrix? By using our second method. First, which operation we need to perform? Our input is here. Our input is here. What is the first operation? H tensor H. What is the second operation? C naught. What is third operation? H tensor H. This product you find out. This is normal matrix multiplication only. After finding tensor product values, normal matrix multiplication. Okay. This is one way. What is the other way? Okay, all of you do it in the first method. That is, apply Hermite gate to this. Apply Hermite gate to this. You find out result. Then apply C naught. Find out result. Apply Hermite to first qubit. So that you will have clear cut idea like which is first qubit, which is second qubit, first system, second system. Okay, maximum 2-3 maximum 5 minutes time. Then no confusion will be there, both methods. Sometimes no, finding unitary matrix may not be easy. Ah, okay. Correct only, sir. Correct. Change, madam. So ఇక్కడ మీకు 1/√2 get 0 plus 1/√2 get 1. Here also 1/√2 get 0 plus 1/√2 get 1. Now that two you combine. Because here you need a 2 qubit gate, no? So you independently you cannot do. You have to mix it. So you write down. That's why that type of doubts you get. No other. Simply, if I explain, you may not be able to understand why this fellow is doing it this way. Correct. What now you write 1/√2 get 0 plus 1/√2 get 0. So this is put parenthesis. Okay. This is first part here. Here, what is the part? Again, same thing. That we write it as tensor product. You put tensor product symbol. Again, same thing you write. Get one. Okay. So now next line equals to equals to this one. This one, if you multiply, what is that? We get 1/2 get 0. Okay. Otherwise, I think I can explain on board that step. After that, they will be able to apply, I think. That only tensor product. No matter. ఎంటాంగిల్ స్టే అదే డెఫినే అంతే కదా డెఫినేషన్ అదే కదా. ఏం లేదు, మీకు టెన్సార్ ప్రోడక్ట్ తెలిస్తే ఎంటాంగిల్మెంట్ అంతే. డైరెక్ట్గా మీరేమి ఎంటాంగిల్మెంట్ క్రియేట్ చేయరు కదా అది. అండ్ ఐ డోంట్ నో విచ్ డిపార్ట్మెంట్ యు ఆర్ ఫ్రమ్. Then electronics means you might actually this Bell state using this department people and all. They even electronics also I think you people might do this entanglement that physically they have to create between two systems. అంటే మ్యాథమెటికల్గా చెప్పాలంటే ఇలా చెప్పచ్చు. లేదు మోర్ ఇన్ఫార్మల్గా అంటే అవి రెండిట్లకు రిలేషన్ ఉంటుంది. ఒక దాంట్లో స్టేట్ మారిస్తే ఇంకొక దాంట్లో స్టేట్ మారుతుంది అని అంటే ప్రాక్టికల్గా అంటే నాకు అర్థం కల అంటే ఆ స్టేట్ ఎంటాంగిల్ స్టేటా కాదా అని మనం చెప్పచ్చు. మీరు అనేది మీ ఉద్దేశం. It appears to be correct only. Okay. Anyhow, I have answer for second. That means first method. Same thing is the answer for second method. See, if you see here, same. This is the order. Hermod. We have already calculated. No. This is first method. First method. First method means not finding complete unitary matrix. That method. First example, it is second method. This example, second method, I asked you to do. Second method means this. We will see that. I don't know. Is this okay? Hermod tensor Hermod, is that okay? Okay. Now C0, we know what is C0. This is our C0. This is Hermod tensor Hermod. This is Hermod tensor Hermod. So finally, no unitary. This is not identity, unitary. This is the matrix we got because 2 qubits means 4x4 matrix we got. Now what is ket 0 0? Ket 0 0, can you tell me what is the answer? Ket 0 0 only. Ket 0 0 only answer. 1,000. What I am saying is this entire circuit, what is the answer? What is the answer here? What is the answer here? What is the answer here? See, after showing this matrix, you should be able to immediately tell. This is the matrix, no? Now what is that you are doing? U on ket 0 0. Our input is ket 0 0 only, no? Ket 0 tensor ket 0 means that is ket 0 0. So U on ket 0. U on what is ket 0 0? 1,000. That means if I multiply U matrix with 1,000, whatever be the first column here, same column I get as answer. Now what is first column here? 1,000. That means 1,000 only I am getting. That means which is same as again same input. Whatever is given, same thing we are getting. Are you? No, this is shortcut I am telling. Otherwise you multiply, you get the same thing. If you have not understood this point also, no problem. What I am saying is, this matrix, if you multiply with any column matrix, with only 1 in that column. Okay? Is this okay? See, U on ket 0 0. U is this matrix. Ket 0 0 is this. Now what is U on ket 0 1? U is the same matrix. 0 1 is. And now what I am saying is, this is some matrix, say. This is our matrix, our column vector. Second entry 1 is there. After multiplying second column, you get as answer. That's what I am saying. Are you? What is the second column, which is nothing but ket 1 1? Are you? What about 1 0? 1 0 is here third position. That means same thing. 1 0 only we get. Ah. We have calculated already here, no? Manually only. Normal matrix multiplication, sir. This is normal matrix multiplication. That I'll explain. Okay, once it is clear, at least we should compare that same answer we are getting. Okay. Is it clear now? Okay, now let us go with the first method. That means individually applying. It is lengthy. First method it is lengthy but not difficult. What is the drawback of this method? This method, okay. See now what is state at T naught? At T naught, what is the state? Time state. Time state. At T naught, what is the state? Ket 0, tensor ket 0. This we can write it as ket 0 or ket 0, 0. These are the. But now I wanted to apply directly. First qubit, this is my first qubit, no? This is second, this is 1, this is 2. Top is 1, I am taking, bottom is 2. From tomorrow onwards, they will say ulta. Implementation, if they, I don't know what they are, if they are use Qiskit and all, accordingly they will use the convention. Don't worry, okay? Okay. Now 1, 2. Now first qubit, which second at time T1, first qubit we are using Hermod gate. Second qubit, this is second qubit, again Hermod gate. What is Hermod on ket 0? What is Hermod on ket 0? 1 by root 2 ket 0 plus 1 by root 2. If you are directly writing, no, you use direct notation only. It will be simple, otherwise big matrices and all, no. Tensor ket 0 plus 1 by root 2 ket 1. Now you again multiply this term with this term. What is that we get? Ket 0 tensor ket 0 is ket 0, 0. Already we calculated, no need to calculate every time. So it is 1 by 2 times ket 0, 0. Okay, if you want, I can write even this way. Directly I can write this way, I think. Okay. Plus first term with this term. What is the answer? 1 by 2. Now second term with first, this term. Is that okay? Now T2. At T2, what is that we need to apply? C naught. Whatever state we got, okay, you give some name to this. This is psi naught state. This is psi 1 state. Simply it is C naught on psi 1. Okay, now what is this? C naught of 1 by 2 ket 0, 0 plus 1 by 2 ket 0, 1 plus. Is that okay? Now by linearity it is 1 by 2, I can take it outside. Ket 0, 0 plus 1 by 2 outside C naught on ket 0, 1. 1 by 2 C naught on okay. Now you tell me what is C naught on ket 0, 0? 0, 0. What is C naught on ket 0, 1? Ah, 0, 1 only. 1, 1. Is that okay? So this is state at T2. This is psi 2. Okay, no, this call it as psi 2 is this much. Now what is state at T3? What is state at T3? That is Hermod on. Okay, directly we will apply. Okay, no, psi 3 equals to First qubit, which gate I need to apply? Hadamard. Second qubit, Hadamard. If you have confusion, this let me rewrite it this way. Ket 0 0 means again 1 by 2. If at all you have confusion, you can separate it like this. Whether I write it this way or this way, because C0, if it is combined, you can view it easily. Here it is separate, you will not have confusion. Okay. 1 by 2, ket 0, ket 1, plus 1 by 2, ket 1, ket 1, 1 by 2, ket 1, ket 0. Because these are the initial examples, no? That's why you might have some confusion. Once after 2-3 examples, you will say whether however you write, no need to write this step like that, you will tell after some days. Okay. Next, what is ket psi 3? At T3. At T3, what is ket psi 3? 1 by 2, first qubit, Hadamard. Second qubit, Hadamard. Like that, all you apply. Okay, this part then you can simplify. No, 1 by 2, one term I'll do. What is Hadamard on ket 0? 1 by root 2 ket 0 plus 1 by root 2 ket 1. Tensor 1 by root 2 ket 0 plus root 2 ket 1. This is for only first term. This is for only first term. Here again, how many terms you get? 4. Here 4, 4, 4. Whatever you do, finally what remains? Ket 0, 0 remains. That means ket 0, 0, it remains. That's all. This is simplification is again how? This is what? 1 by 2 root 2, ket 0, ket 0. This is unnecessary, no. This is easy or the previous one is easy? Again, what is the problem with if I change? If I ask for 0, 1, again everything, entire thing will change. Here if I put 1, gone. Entire thing you need to repeat, no? This method is better, no? Very, very, very much better. This type of example for 4 states, if you do, then it will take 2 hours, 1 hour at least. Are you okay? Next one. Is the procedure clear now? Okay. Now all of you calculate this. What is Hadamard on ket 0? Is that correct? Can we write? Okay, this shall I erase this? Okay, this. So can we say, can we write this something like this? One by root 2 whole power 1, ket 0 plus ket 1. Is this correct? Both are same, no? So can we write it as 1 by root 2 whole power 1 sigma x belongs to 0, 1 ket x. Same, no? Okay. Now I am going to use short form like this. 0, 1 square means all binary strings of length 2. Now you tell me what are the possibilities? Okay, 0, 1 cube means how many entries will be there? 8. Now you know the algorithm. Now tell me what is, okay, what is this value? Please calculate. Hadamard tensor 2. which is same as Hadamard tensor Hadamard ket 0 0. This is the meaning. Hadamard tensor 2 means Hadamard tensor Hadamard ket 0 0. What is Hadamard tensor Hadamard? We have already calculated. Here. One by two of 1 1 1 1 1 minus 1 1 minus 1. Okay. What is ket 0 0? What is this value? What is this value? Can we write it something like this? 1 by root 2 square sigma x belongs to 0 1 square ket x. Is that okay? That means Hadamard gate, if I apply on ket 0, it puts all possible states, single qubit, all possible states in equal superposition or not? What is the probability of getting 0? What is the probability of getting 1? 1 by 2. 0, 1 are the only possible states if it is a single qubit system. If it is a 2 qubit system, what are possible states? 0 0, 0 1, 1 0, 1 1. Okay. Now what is the probability of getting 0 0? 0 1? All possible states it puts in equal superposition. Are you similarly, can you guess what is the answer for this? One by root 2 whole cube ket x. So that means what? All possible states, all possible 3 states with 3 qubits, it puts in equal superposition. Are you okay? Now, if at all you have a graph, something like this. I just wanted to find out you know what is dominating set? Okay, that I will tell you. A, B, C, D, E, F, G. What are neighbors of A? That you know, no. What are neighbors of A? Which are adjacent to A? B, E, F, G. Now it is there. Okay. Okay. Correct. Earlier it was not there. Okay. Okay. Yeah, at least now you know the meaning is clear. Okay. Now our goal is to find some subset of vertices here such that any vertex which is not in the subset, it is adjacent to at least one vertex in the subset. Or simple terms, if you want, you in the class, some class, BTech class, you just wanted to find out subset of students, select some subset of students such that every student who is not given chance, that means not selected, is having at least one friend in the selected students, so that they will not complain about selection. Okay. What is that we are trying to do? We are finding a subset of students in the class such that every student who is not in the subset is having at least one friend in the selected students. Friend means there is a line. Here there is a line means they are friends. A and E are friends or not? No. A and B are friends or not? Yes. Is that okay? Now we need to find a subset of vertices here such that what? Any vertex which is not in the subset must be adjacent to at least one vertex in the subset. Can you give me one such subset? AE if I take, is it satisfying the condition? No. No, thank you very much, sir. AE is not the required set. Why? Because C, no friend is there in the selected group. We don't want this type of set. Now that fellow also we include. Now, is it our required set? Yes. So that means total how many vertices are there? 1, 2, 3, 4, 5, 6, 7. 7 vertices, no? Order you put A, B, C, D, E, F, G. So each one is either, now in this case, A is 1, C is 1, E is 1, others are zeros. Is that okay? This is the possibility. Now, I just wanted to find one such set, but that set cardinality must be minimum. How many possibilities I get? For each vertex, there are two possibilities. It may be there or may not be there. Maybe there, may not be there. Maybe there or may not be there. Maybe there, may not be there. Maybe there or may not be there. So two possibilities here, 2 power 7 ways it can happen. No? Among all these 2 power 7 ways, one or more ways is our actual optimal solution. Okay. So in many quantum algorithms, the starting point is you start with all 2 power 7 answers. And each answer you give same probability. Like for example, if I have 4 answers like this, each one can have probability of 1 by 4, 1 by 4, 1 by 4, 1 by 4. And this is the starting point in many quantum algorithms. So anyhow, maybe next 4 more days, they explain definitely at least some quantum algorithms they explain. No, this is the starting point. They put all possible answers afternoon, whatever you asked also. Okay, all possible states in equal superposition with the hope that all have equal chance of being selected as our candidate or optimal solution. Then what they do is whichever has higher probability of close to the solution, their probabilities they increase. Which are not good solutions, their probability they reduce. They become close to 0. Which are good, they become close to 1. Finally, they return whichever has the highest probability. That becomes our optimal solution. So problems, they solve it this way. And this is the starting point, as I mentioned, in many quantum algorithms. Deutsch algorithm, Deutsch-Jozsa algorithm, Bernstein-Vajrani algorithm, Simon's algorithm, Grover's algorithm. This is the starting point. Okay. Okay, same thing we can write 1 by root 2 whole cubed, as madam said, 1 by root 2 whole cube, sigma x belongs to 0, 1 whole cube, ket x. This is only all possible states, 8 states in equal superposition. Similarly, this one, 1 by root 2 whole power 4. And this you see in many algorithms. Many algorithms, that point you see. In general, they write instead of 2, n. Okay. Okay. Similarly, for n, this. Those who have difficulty, you can refer to this. Now ChatGPT is there, anywhere you can refer, okay, or some other you can use. Even you can write, no, this line I have not understood. You please explain in detail, in simple terms. Then it explains. Even if you want to make it more simple, you make it even more simple, like for 5th standard student also understands. Then it explains. If you want even better way, you can see, give an analogy so that we can understand. So that also explain. Now we have very good teachers. Okay. Okay. Correct. No. But we should know how to ask it. That's all. Prompting. Prompting, if you know, then over. Okay. So this is for 3. This is the way we get. This is ket 0, 0. This matrix is 8 by 8 matrix. If you apply all ones, this is only answer, no? Okay. So what is that we have discussed so far? We have started with, okay, anyhow. Already in the previous session, we started with what is quantum computing. Okay, 2-3 minutes I summarize. What is quantum computing? It's a computing based on principles of quantum mechanics. What is quantum mechanics? It is a branch of physics which deals with particles at the smallest possible level. Okay. Now, what are principles of quantum mechanics? Superposition, entanglement, quantization, okay, wave-particle duality, like this. There are different principles of quantum mechanics. Now, why quantum computing? That means there are some difficult problems which, even if you consider fastest supercomputers in the world, which are based on classical computing, they fail to solve. One such problem is integer factorization problem. But quantum computers, By using Shor's algorithm, Peter Shor's algorithm, they can easily solve this integer factorization problem. So if integer factorization problem is solved easily in polynomial time, RSA crypto system is at risk. So for that, people started developing post-quantum cryptographic algorithms. That is new area of research. But what is the immediate threat to us? We should not use cryptographic schemes which are based on this integer factorization. Okay, if there are other algorithms also, we should not use that. But what is the advantage we have now? It is in the really infant stage of quantum computing development is very infant stage, so we need not worry. Still some more years, these algorithms will work. And anyhow, people are doing research on post-quantum cryptographic algorithms. That is about, so finally, there are some difficult problems which classical computers are not able to solve, but quantum computers can solve it in no time. Okay, that is why quantum computing. Next, we started what is NQM and Amaravati Quantum Valley. That is okay. Next one is what is qubit. It is a column vector where all entries are complex numbers and sum of absolute valued squares of all entries equals to 1. Okay, no. Then that is called quantum state. What is qubit? If number of allowed states in that quantum state is only 2, then in that quantum system is only 2, then that is called qubit. General form is alpha ket 0 plus beta ket 1. What is alpha, beta are called probability amplitudes. Okay, mod alpha square plus mod beta square equals to 1. If I go for measurement, what is the probability of getting 0? Mod alpha square. Probability of getting 1 is mod beta square. Once we go for measurement, this quantum nature is gone. We'll get classical outputs. Then we talk about, we understood that all quantum operations are reversible and they are represented by unitary matrices. Okay, a matrix, square matrix U is said to be unitary if U times U dagger is conjugate transpose of given matrix equals to U dagger times U equals to identity. Okay, that is called unitary matrix. All quantum operations are reversible and are represented by unitary matrices. Then we talked about quantum X gate. X gate, what is the matrix? 0, 1, 1, 0 is the matrix. Similarly, Hadamard gate 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. And we have given some circuits, then how to find, if there are any circuit involving this, how to find the answer output. There are two different methods that we have seen. Next, finally, what is that we are talking about? Tensor product. What is tensor product? When do you say that a quantum state is a product state? When do you say that it is an entangled state? Okay, so that means entanglement we discussed more formally. Superposition also more formally, linear combination, this also more formally as tensor product. Okay, that's what summary, this is this. And these are the resources. Mainly, most of the things I learned from this. IBM Quantum Learning course website we have. There are different courses, only 2 courses I use, Basics of Quantum Information and Fundamentals of Quantum Algorithms. There are 4 lectures in each, 4 lessons, 4 plus 4, total 8 lessons. That 8 lessons, after understanding that, whichever textbook you want, you read. Here they have very neatly, John Waters, very neatly explained and nicely in simple terms, without assuming any background, they explained. And this is standard book, I agree. And you open and see your feeling, okay? Okay. After learning from other sources, then you can start reading this. And this is one resource which I found while searching online. In 1 hour, less than 2 hours, they explained entire quantum computing. Very, not detailed, this is little fast, but they covered everything. But to understand it, we should have minimum knowledge. Only 1.5 hour, 1 hour 40 minutes, I guess. Yeah, less than 2 hours. Quantum source. Okay, no? You type in that, you will get it. And thank you very much. Once again, I thank the organizers and Gurrao sir and Madhuri madam for giving me this opportunity. Okay, thank you very much. Thank you, sir. Thank you. And you are interacting with me. That is very good thing. Otherwise, online, no, most of the time it is one way. Okay. Oh, sorry. Thank you. వాళ్ళ ఇష్టం ఉండండి వాళ్ళు.
Sir, thank you so much, sir. Let me take the immense pleasure in thanking our esteemed speaker, Dr. P. Venkat Subba Reddy garu.